Okay, so now we have Marcus Hutter, who is...
Another change in schedule.
Another change of schedule. So first we're going to have Marcus Hutter, and he's going to be talking about the future of artificial general intelligence, is that right? And society, yes. So as you may know, Marcus is a professor at ANU and is also the author of the UAI sort of idea and the first formalization of general intelligence. So put your hands together for Marcus. Thank you.
Okay, thanks. So you see how far we get, so we can't even, make a projector work, right? But, and it doesn't work here, so I have to look around here. Okay, since we are late, let me start, and I hope I finish a little bit early. So I will talk about the future of AI and society. I like science and try to stay away from politics, but the further the career progresses, the more and more you're asked about these questions. What implication does it have? These are valid questions, so I will talk a little bit about it. Although I usually, like to refrain from answering these questions. What is artificial intelligence? So there are many views. One view which many people hold, they don't express it explicitly like that, but they say, if a machine can do X, then X is not artificial intelligence. That's a view many people hold. I will come back to that in a second, and you will see why. A machine that passes the Turing test is intelligent. So Alan Turing came up with the imitation game, which is not too bad, but it's more a test of humanness rather than of intelligence. So how smart is the system to fake a human, which needs a lot of intelligence, but it's in some sense too strong and too weak. There's a nice quote from John Neumann, who invented game theory. If you tell me precisely what it is that a machine cannot do, then I can always make a machine that will just do that, right? So if you would say vaguely a machine cannot do this, this is just a sentence, no meaning. If you precisely stated mathematically what a machine cannot do, I can make a machine which just does that. It's not strictly true, but it has some truth in it, so it's a nice statement. For this talk, I will use a definition which is much more fruitful. Intelligence measures an agent's ability to perform well in a wide range of environments. I will have little time to sort of explain and motivate this. At this point it's just words, but they're very carefully chosen, and there's a mathematical theory which makes this precise, and I will very briefly glimpse the equation. So here are some past successes of AI. Checkers in 1950s, great, played checkers. Oh yeah, it's just just search, and it's not really AI, right? Expert systems, yeah, that's not really AI. I mean, it's just logical rules and deduction, so that's not AI. Backgammon, that's what dogs do, reinforcement learning, that's not AI, right? Automatic theory improving, that's what mathematicians do, right? It's just rule symbol manipulation, that's not real AI. Operations research, routing of trucks and so on. Yeah, look, that is useful application, but that's more optimization, it's not really AI. Chess was once, thought of a game where you need a lot of intelligence, but no, it's just search, some heuristics, that's not real AI, right? Speech recognition, that's just a hidden Markov model on neural network, and you train a little bit of parameters, that's just statistics, right? Self-driving car, well, maybe, it's not too bad, but driving a car, I can do that in my sleep, yeah. Nearly in my sleep, yeah. In my unconsciously, it's not really AI. So that's how people argue that as soon as a machine can do X, it's not it's not to do with intelligence anymore. And if you take this definition, then we will achieve, of course, never AI. Yeah. So just continue this belief, and then there's no risk, right? That AI will ever work. So here are some more recent successes, but it gets harder and harder to argue, right? So IBM Watson beats the human in the Jeopardy quiz competition. That's quite nice, right? Although, in a sense, it's just a huge database and lookup, and some text processing, but it's impressive, yeah? You can play perfect Texas Hold'em poker now nearly as well as a human being. You need bluffing. I don't know much about these games, so it's in a sense sort of more difficult than these full information games like chess and Go. DeepMind in 2015 developed a deep Q network which can play Atari games, so these old computer games from the 80s, and 25 of them, on a human level, if you're a little bit generous with what human level means. Then AlphaGo, you've all heard about AlphaGo, beating the world champion in Go. I think really impressing engineering, putting lots of modern techniques, deep neural networks, reinforcement learning, and all kinds of tricks together. And it was a surprise because people believe that Go is, takes a couple of, years or maybe 1 decade more. Again, if you look into the system, right, okay, it's a deep neural network, and then there's reinforcement learning, and you do this and this and trick, is that AI or not, right? But in the end, we will have achieved systems which outperform humans in many areas, most areas, by a large margin. And then you will still argue, if you look in the system, it's not really AI. But if you look in our own brain, it's the same. It's just neurons and firing patterns, nothing more, right? So this argument really doesn't succeed. So there are many approaches to AI and to superintelligence. So we could scan our human brain and simulate it in 10 times speed, right? We have achieved AGI. I think that's sort of the easiest path, just a little bit of engineering. Genetic enhancement can lead to a little bit superhuman intelligence, but has, I think, limitations. Brain size, is sort of limited. Brain augmentation is a very interesting path. Peter Cheeseman has talked about it, I think. That we sort of, have chips, we communicate, with, the internet, and, at least the knowledge we don't have to store in our brain. Simple arithmetic operations, we use a calculator anyway. We can ask deeper questions, we use theory, but just thinking. And, maybe more and more we do with this extended brain. And, at some point, maybe we reach a level where I think, oh, I haven't used my own biological brain in the last 2 years, right? I delegated everything. Maybe I can switch off this small part and I don't need it anymore. So that would be a graceful way of becoming, cyborgs or beyond cyborgs. Okay. Well, these are natural approaches. I'm not working on that. But these are approaches which are valid and may succeed. Then the artificial approaches. That's sort of along the history. We had logical-based reasoning systems, expert systems, and then economics-inspired systems, based on game theory, decision theory, and utility. Cybernetics was inspired by engineers, so adaptive control theory, and humans are also sort of adaptive control systems. Machine learning, the modern approach. I mean, it's very hard to build this sort of intelligent system. It's easier to build in sort of a baby which then learns from experience, an official baby. Information processing becomes more important. You think that should have become more important earlier because a computer is an information processing quantity. Humans also information out, information in. But this paradigm just has recently become more and more important. So separately, these approaches will probably not succeed. So you have to probably somehow combine them, either in a say messy way, and I don't mean that negatively. So that is maybe more Ben's approach, right? AI is complicated, and you have to put all kinds of modules together. And a clean approach is nice in theory, but will not work in practice. So that's my approach. I like it clean and neat, but Ben likes it to work, right? So my approach was, we work on AI, and people don't know what intelligence is, and often a field gets really boosted if you define the key quantities. In physics, at some point we knew what energy means. It was a mysterious quantity, and then became a completely formal mathematical concept. And you have the first and second law of thermodynamics, perpetuum mobile don't work, and so on. So it really helped the field. So I think, I thought it will help the field if you have a formal mathematical definition of intelligence, which captures all aspects of intelligence, or at least the aspects we care about, so rational intelligence. And I've done that around 17 years ago, and these are the principles you need to combine in order to achieve this definition. So there's Occam's razor principle, Epicurus principle, Bayes rule, Turing machines, Kolmogorov complexity is a measure of complexity, a general measure. And Solomonov already 50 years ago solved the problem of induction, how to predict well if you don't know anything about your data. So if you want to predict stock market, use Solomonov. Nothing can beat Solomonov. If you want to predict the weather, use Solomonov. Nothing can beat it. It doesn't mean that it works, but it says if anything works, this works at least as well.
Within some constant,
Yeah, with some constant, yeah.
which is bigger than the universe.
No. These constants are, for the prediction part, really small, you know, maybe 10,000. That means if your data size is of the order of 10,000 bits and larger, it's fine, right? And nowadays, you know, 10,000 bits is nearly nothing. There are some theorems where these constants are, you know, like Levin search, where they are ridiculous. But in Solomonov, no problem. The problem here is that it's incomputable. So it's an Etherium mathematical theory, but you cannot directly implement it. You need to approximate that. But people have done that. But beyond prediction, we also want to act, and then the environment reacts back to us, and there we need so-called Bellman equations to make that work. So if you combine all this, you can define a measure of intelligence. It's repetition of the informal definition. Intelligence measures, or is the intelligence ability to achieve goals in a wide range of environments. And this implicitly captures most traits of rational intelligence, if not all, such as reasoning, right? To achieve goals, you need to reason, right? You need to be creative to come up to solutions. You need to generalize what you've learned from one situation to another. So in order to achieve this informal, what the informal definition says, you need to be able, the agent need to be able to plan, to learn, of course, to preserve itself, and so on. So these are all emergent phenomena of this definition. Okay, so makes intuitive sense, but the real important point is that this has been rigorously mathematically formalized. So there's a mathematical equation, and you can rigorously prove that all these, well, you have proofs for most of this, not all, that these are emergent phenomena. Okay, and it has a lot of positive properties apart from capturing all these aspects of intelligence. So it's non-anthropomorphic. There's not a human in the loop, for instance, you know, like in the Turing test, right? You know, it's general, unbiased, fundamental, blah, 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 and so on. Lots of nice properties. So in any case, it's the most comprehensive formal definition of intelligence which is out there so far, and for the last 15 years nobody has come up with something better and didn't poke a serious hole in this definition. Okay, and sort of it assigns a real number to every agent between 0 and 1, namely to the expected performance averaged over all environments, all problems the agent potentially has to deal with. This is infinitely many, so you need a bias towards simple environments. And discount complex environments a priori if there is no evidence for them. And that is sort of implementing Occam's razor, which is a very important scientific principle, maybe the most important one. Okay, so then you can turn it around. If we can measure intelligence, then we can ask what is the agent which is most intelligent with respect to this measure. So if this measure is good, then we get a really very intelligent agent, and you can put this equation in one line. And that's this equation here. And I will not go into that. So this is sort of the planning part, and this is here the learning part. So you need to solve the planning and the learning problem simultaneously. Yeah, you can read more about it elsewhere on our website or in numerous publications. Okay, the problem, it's incomputable. So you cannot just throw it into your computer and run it. So if you had infinite computational resources, we would already be there. The good thing is now we have just transformed a very difficult conceptual problem. What is intelligence? What should we do? To a computational problem. This is what you should do. It's just too slow. It's like with chess. Minimax to the end is the optimal strategy. Easy. We just need a more efficient algorithm, and a lot of work had gone into it. Yes, to make this efficient is very hard, but it's good to have a starting point. Yeah. And we have made approximations, but which are sort of very limited. But okay, that's sort of the gold standard. This is what you want to achieve. So if you could run it, we have the superintelligence already here. What is nice is, so interestingly, the philosophers have first picked this equation up, and now they're discussing AGI safety questions and other questions in the context of this equation. Okay, look, we have here a superintelligent agent. What would he do if he let it loose? And you can sort of analyze it theoretically. Yes, we can never achieve that exactly, but we can get closer and closer to it. So, can we get there? I mean, you probably have all seen Moore's law. We have had different regimes, you know, electromechanical, then relays, then tubes, transistors, integrated circuits. So there's a little bit sort of steam lost in Moore's law in the recent years, but parallel processors and GPUs, so that they can catch up. You know, at some point we have, you know, billions of cores in parallel, And if this runs out of steam, then hopefully we have quantum computers, although we probably don't need them for human level AI. So we already have, so if you take all computational power in the world together, I think already 5 years ago, or maybe 10 years ago now, we surpassed the capacity of one human brain. Yeah? So it's still sort of some imbalance, right? But we already have the computational capacity, and Google probably owns, I don't know, 10% of all computational capacity. So probably soon Google has the capacity, right, to simulate one human brain. So even if Moore's law stops, we could achieve it. Although I hope and believe that it will go on for many decades more. Here are some, it's hard to predict, especially the future. So here are some predictions about future AI successes. So self-driving cars, I mean, that works, so they should be there in the 2020s or so. It's more or less sort of a legal problem. Automated surveillance, London, I think, has more surveillance cameras than people living there. And the problem is somebody has to view all this material, but if you use AI to sort through that and just flag, suspicious behavior, then we can become a totally surveyed society, which many people, including me, don't like, but this will come. Yeah? Because the argument is always very simple. Oh, there was a crime, it's unsafe, we need surveillance camera. Yeah? And at some point we will also have surveillance camera in the toilets, and then the last thing is probably the bedroom. Because all crime happens where there are no surveillance cameras, right? So you always have to put more and more and more. So think about it. And it's not bad governments who want that. I mean, they maybe want that. It's the people, you, who want that. Personal assistants, I mean, we have already Siri and so on. They will get better and better. Household robots, maybe 2030s. Chip implants. For disabled people, we have that already. It's very limited. But I could imagine that in the 2030s, the technology is good enough that everyone wants that. Decision support systems, I mean, we have that already, but in more and more industries. So, really making high-level decisions. So now our activity will be saved from automation. That leads me to the next slide. So in order to talk about society a little bit, one point which annoys me a lot when discussing unemployment, the unemployment rate is too high, we need to lower it. Unemployment is bad. Unemployment is not bad. Yeah? It's the question what we do with it. So let me argue here about it. So or underemployment. So in the long run, no job is safe for automation. But the point is, if one job gets lost and it's automated, we still produce the same goods and services. So we still can live equally well off on average. It's only a question how to redistribute the money or the resources. So we are not worse off. Yeah? So the overall living standard can stay the same. And if some of these people who lose their job get other jobs, not all, even only 20%, so the living standard can even rise. Yeah? So, and there are lots of solutions. We can reduce the weekly working hours. We can, have early retirement. We just accept unemployment and have sort of very nice unemployment benefits, right? Just keep them up, and we can afford it because the machines produce everything. Ultimately, if the machines produce everything, nobody has to work and everyone can have an income. Yeah? It can cause problems, but it's not as bad as people think. So all these scenarios, right? There's also a possibility that become more and more inefficient, right? That would be not so good. Problem is the transitional phase and to get it right, but it's a political problem. And I think it's not too hard to get it right. So don't worry about unemployment in the long run. So you should embrace it. Okay, so then in the longer run, right, at some point machines take over or we merge with the machines. So you have heard about the technological singularity already. There's a definition, and then we cannot predict anymore. And might just skip that because I run out of time. So here's some other societal implications. So I talked about underemployment. I think it's inevitable, desirable, and affordable. So another one is the value of life declines. So that is something which is somewhat sad, maybe. But think about books. When books came first out, they were handwritten, very valuable, very expensive. Nearly nobody could afford it. Then came the printed press that became cheaper, right? Then come the electronic books, right? You can just download the book, just read it, throw it away, yeah, often for free. So as soon, the easier it is to copy something, the less valuable it is. And you know, it was nice to have these nice books. They were expensive, they had some value, but do you really want to go back to this time? Yes, books became sort of a throwaway commodity. Okay, so once life becomes virtual and we can just copy it in the computer, I predict that the same will happen. You know, I go out, do some bungee jumping, it's fun. The rope breaks, I die. Not a real problem, I have a backup at home, right? I just re-instantiate it. I have to do a lot of research. I make a couple of copies. Someone on the street kills some of my copies. Not too bad, right? I'm still there, right? I can do the research I want to do, I think should be done. And I think then, once you get into this mentality, you think, okay, even if I'm killed, it's not too bad, right? I mean, I have a clone here. It just continues with my stuff, you know. I'm expendable. So in the long run, probably the value of life goes, you know, significantly down. And a lot of our society is based on that human life is valuable. You know, think about safety and, you know, moral laws, you should not kill and all these things, yeah. And if the value goes down to close to zero, then our society will change a lot. So that's another prediction I make. There are some other things. You know, if you have multiple agents, there will always be competition, and evolutionary pressures should then breed agents which compete, and if they live sort of in a computer, about computational resources. You know, there will be sort of always scarcity in computational resources. Peter said we have more computation power than what we know what to do with. I think that will never be the case. It's not true now. There's always more you can do. In worst case, you just play computer games with really good graphics. Immortality, I mean, you can become immortal. This also has drastic consequences. Assume you know that you're immortal. Oh, why should I hurry start in 5 years? I can just take 50 years, just make 10 years holiday, then return, right? So it will also change the dynamics a lot. Values and morals and ethics, you know, what do we want to survive in the long run? Most people are conservative and say, okay, the ethical system now is good, you know, everything else is bad, right? But, you know, this changes slowly over time, and as long as sufficiently slowly, you know, usually it's sort of regarded as an improvement. Not sure, you know, what will happen. Another interesting question is, do we have a choice, right? And, you know, there are evolutionary market forces, and again, Peter said, right, in principle you could say, no, we don't want this new technology, right, it's dangerous. But I want my next smartphone, I want a better Siri, right? But I don't want the new technology, right? That doesn't go together. I think we have very limited control over the future technology. Society may be completely different. So there's the runoff effect, so the company who invents AGI first, you know, dominates the world, and there will be only one intelligence which has very different consequences. So there's no evolutionary pressure, so that would be a completely different society. Okay, I think I'm done here. So these are a couple of books. So Nick Bostrom, a philosopher in Oxford, wrote this book, Global Catastrophic Risks. You know, and you know, global and catastrophic means really wiping out humanity, or setting it back for hundreds of years. And one is AI, but interestingly, AI has also can lower the risk, because you can use the AI to lower all these other, I think, 19 risks. So on balance, it's not so clear whether AI causes higher or lower risk. So he also then later wrote this book about superintelligence, which nicely summarizes sort of block discussions of the last 15 years about, you know, singularity and likelihood and what it implies and so on, and you know, some own thoughts also. That is my own research. Don't buy this; it's incomprehensible. But this is my first PhD student who co-founded DeepMind, by the way, and he wrote his PhD thesis in the book, which is a much more accessible explanation of what I'm doing. I mostly prove theorems, right? So completely useless stuff. And I think I should stop. And there is Ray Kurzweil. Probably most of you know this book. He wrote about in 2005 about the technological singularity and popularized it. But I would like to point out there was a book by Hans Moravec, 1988, so much earlier, who already foreshadows the singularity. It's actually a quite neat book. So if you want to read another book about this, maybe more balanced view or so, but also very positive, then this one, read this. It's still a nice book, I think.
Not to
Thanks.
mention a couple of conferences there.
Yeah. So these are not books, and I didn't have time to update them. So that is great that we have Adam here, who organizes every year either a singularity conference or science, technology, and future. Without him, sort of this event would not be here. And yeah, we are now in 2017. I update my slides next time.
Okay.
Thanks for your attention.
Thank you. We have time. We've got time for one question while Joshua Bark just sets up quickly. And yeah, depending on how long it takes to set up, maybe we have time to two. Let's see. Okay, who wants to ask a question? Ready? Set. Okay, over there.
You mentioned about how we'd be able to redistribute kind of the gains to sort of ease the problems that might be caused by unemployment or underemployment.
Yeah.
I guess traditionally that role has been taken on by governments, but there's a good chance that with the invention of AI, there's going to be a big shift of power away from governments. And do you think they'll actually be able to enforce any redistribution of wealth away from the people who have benefited from those advances?
So if we're talking about AI, subhuman level, but pretty smart but subhuman, I think it's not much different from, say, the Industrial Revolution, right? You know, the power shifted also to the manufacturers, and then government stepped in, minimal wages and so on, and we are better off than before. I think the same will happen with AI, as long as it's subhuman. As soon as it gets human and superhuman, all bets are off.
Okay, another one? Over here?
What's your view of substrate independence?
Yeah, I think
Randall
intelligence
Coase.
is substrate independent, yes. And even consciousness, I would go that far.
Questions? Wow. Okay, one over there.
If we've tended to overestimate how quickly the changes are coming in the past, and now people are telling us that we're underestimating how quickly the changes are coming, what is fundamentally the thing that's changed that has made that switch in your mind?
Well, in AI, we always overestimated how quickly it comes, and it was always sort of, it's there in 30 years, and that has been for 60 years now. So in AI, I mean, sort of on average, people have
it's
not
working here. It's working here, but all you need to do is turn that one on.
underestimated that. I mean, at the moment, there's quite some hype, and maybe the people who believe that AGI comes have a larger voice now. Or are you referring other technologies and comparing that to AI?
In particular, AGI, we're being told that one of the earlier speakers said we used to think it was going to come quickly and it didn't. Now we think it's not going to come quickly and it will. So
No.
I guess the question is, do you believe that? And if so, why should we think?
Now, who
it's gonna
says
come
that
quickly?
they don't believe that it becomes quickly? So there have been several surveys in the last sort of 60 years, and you know they were not systematic. Sometimes just AI professors, and sometimes the general public, and so on. But it seems very roughly people always believed it comes in 30 years. So I don't think that on average people now, whatever people means, does it mean AI researchers or the general public, believe now that it takes longer than they believed? On the contrary, I think the belief now, especially with successes like AlphaGo, self-driving car, more and more people believe that it becomes quicker.
Okay.
I think what he was asking is, if before people kept saying it was going to come in 30 years and it didn't come, why should we believe now that it's going to come in 20 years when everyone's estimates were wrong before?
Sorry, I misunderstood you. I would mostly refer to Moore's law. So in 10, 20 years, we can have affordably the computation power of a human brain. And I said we already have the computation power, a couple of human brains, but that's not enough. We need to experiment. We need thousands of brain capacities, play with the parameters, have new ideas. And Given the problem we have solved, speech recognition, self-driving cars, so these are now slowly problems which traditional approaches, had lots of difficulties like vision and audio system. There's also another estimate about, so speech recognition, I think, don't cite me, and that needs 1 cubic centimeters of our human brain, and needs so and so much computation power. So if you extrapolate that, right, it is another data point that we should soon have the computational power. Of course, that is not enough. We also need the right algorithms. So maybe we have the capacity, but we never figure that out. But then we have the sort of the boring approach. We just scan the human brain and simulate it. Of course, we also need technology there, but that seems to be much more, in a sense, predictable. You don't need a groundbreaking new insight. I mean, engineers also have insights in order to get better scans, but it seems to be more plausible that this should happen at some point, that we can just scan and simulate the human brain, and then we're also there.
Okay.
And there's also Moore's law about brain scan resolution. So Moore's law.
Thank you, Marcus. Put your hands together for Marcus Hutter.